with the insertion of a Wilson loop was going to be equal to the Kaufman bracket for this knot of x after doing two things. Firstly, a substitution of the form x is, I think I got something a little wrong in this. X is some exponential of 1 over h bar with some factor. And two, possibly normalizing by x to 3 times the right the knot. So the framing is always a little tricky to deal with in this story. So I realized yesterday, I was reading Witten's paper, Quantum Field Theory and the Jones Polynomial, and he pointed out a kind of clever way in which you don't have to worry too much about the framing. So this here depends on a knot with a framing. But Witten points out...
Sorry, I was normalizing by x over what?
X to the 3 times the writhe.
Oh, okay, I see.
So this is the expression that we calculated by looking at this knot and realizing the answer of this was x cubed or x minus 3. So if you multiply it by this, you get the same as the on knot. So Witten remarks, every knot in the 3-sphere, or 3, has a canonical framing so that the self-linking vanishes. That's a way to normalize the framing. So if we use this framing, then the Q of t gives rise to a knot invariant without framing. Okay. And if we use this normalization, then, well, on this side here, we should put x to the 3 times the writhe, because this expression, this is normalized to be a knot invariant.
Sorry, what's the self-linking?
Sure, the self-linking is so we take a framed knot and you displace it from itself using the normal vector to get some k prime, and then the self-linking is equal to the linking number of k and k prime, as we defined in our exercise, so like the original knot invariant discovered by Gauss. So, for example, if I use the circle, the on knot, with this inward pointing framing. This is no self-linking. So this is the correct normalization. Because if I take the circle and move it in a little bit, it doesn't intersect with itself. But if I take this knot, and I use the framing given by the blackboard, where I have this vector, well, so it's a little hard to see, actually, but this will have a non-trivial self-linking. Recall the linking number is I take my two knots, and I look at how many overcrossings or undercrossings they have. So we did this in one of the exercises. But this expression will have, I think it has a self-linking. Okay. So this Kaufman bracket, it was defined by this local rule. Something like this. Well,
Kevin?
Yeah?
Can't since to study the self-linking, we only care about the over and under crossings. Can we just draw the circle by draw framing that sort of like vanishes at some point and then goes the other way?
Like where it points into the blackboard at some point? Yeah.
And then when you shift it, it's clear that there will be an under crossing.
Yeah, that's a good way to do it. Yeah. So you'd say here at the bottom it points down and over here it points up. But as I go over here, I'm going to have to go into the blackboard. And then if I look at the plane of projection, there'll be some crossings. Absolutely.
Is there any forms that I can integrate over the link to determine the self-linking? Is that just the spin connection?
No, it's a U1 thing, right? So like the linking number is associated to the U1, the expectation value of a Wilson line for U1, because I have two knots and I have my propagator connecting them and I integrate over the two knots. But the self-linking is also the same kind of thing. So the self-linking is like a regularized version of this diagram. Take my knot, and I have my 2 points in it, and I'm exchanging a gluon for U1, for the group U1. So the self-linking will appear if I study the Wilson line for U1, because that involves the trace of the exponential, as it involves the exponential of the integral of the curvature. So there'll be points where I integrate here, and they can exchange a gauge field. And to regularize this expression, I move one of them off a little bit. And it becomes the self-linking. Yeah.
I'm a bit confused because like this notion of self-linking is dependent on like where you're viewing from. So why does that enter the picture?
So it depends on where we reach. So where we.
Because it depends on the projection. Like
No, it doesn't. It doesn't. The linking number, the definition of the linking number for 2 knots. There's just an integral formula.
here we just have one knot, right? And then we're defining self-linking for a single knot. And if we were to view this knot like from the top, then we wouldn't see any like.
No, it does. It's just hard to see it in these pictures. Maybe I can try and draw it a bit better on a different blackboard. It's just, I mean, it's hard to draw the 3-dimensional pictures. So let's try. Suppose I just take this knot in R3. And suppose my framing winds around once. So my framing goes down, and up here it goes kind of into the blackboard, out, and then in, so on, and winds around. what does my, if I displace it by this guy, what does it look like? Here, well, here it goes, it's really a three-dimensional thing. And here it might go over. And if my framing winds around that way, it goes under again. You see? So the displaced knot can be thought of in purely three-dimensional terms. I have a three-dimensional knot with a normal vector, and I displace it. And then I use the Gauss formula for the linking number. And you can kind of see that it's really closely related to how many times I wind around. So why would you have anything like this from quantum field theory? So to make this work, you'd want to So Witten explains in his paper a rather beautiful argument for why thinking about quantum field theory will lead you to a relation just like this. However, the version Witten uses, so there's two slightly different presentations of the same knot invariant. One uses this relation, and the other one uses something which is almost the same, but slightly different. So we're going to use the slightly different version. So it turns out we get an equivalent knot invariant as follows. We let L plus be I hope I'm going to get this conventions right. L minus be where this guy goes under, and L0 be this one. So you notice that this one is nicer in some ways because, well, from the point of view of quantum field theory, it's going to be useful to have our Wilson lines to be oriented. And this one plays nicely with oriented lines. That one doesn't work quite as nicely with oriented lines. And then so the Jones polynomial satisfies the local rule So this is the same as minus x times 3 times the right of the Kaufman bracket if t to the minus 1 over 4 is equal to x. So it's just another way of redefining this, doing the same thing, just with using these three these three kind of elementary moves instead of those three. So we would like to show that the quantum field theory invariants satisfy the same relation. Well, how do we do this? So the key point is going to be to understand, well, here I've written these local moves on a knot. We can imagine some complicated knot living outside this little circle. So to be able to understand some relation like this, we need to understand the locality properties of quantum field theory. How the quantum field theory invariant can be built up from pieces attached to individual crossings. So that's the way quantum field theory invariants glue together is well studied under what's called axiomatic quantum field theory, or axiomatic topological field theory. This requires this is axiomatic topological field theory is an important topic in its own right, so it's good that you will be exposed to it. So this is the Witten Attia Seal axioms for a 3D oriented TFT. So the first piece of data, for every surface, every oriented surface, we have a Hilbert space. I'll just call it a vector space. H of sigma. Now, so what this is to be understood as, we have a three-dimensional theory. I can ask Hilbert, what is a Hilbert space on some space-like slice? However, people commonly use the word Hilbert space to refer to this vector space, but this vector space is not a Hilbert space in the sense defined by Hilbert. It does not have an anti-linear inner product on it. And I hope we can see why in a minute. If I take two disjoint union of two surfaces, then the Hilbert space is a tensor product. So this is, if you like, this is kind of what the kinematics is. I haven't talked about any time evolution or anything like that.
These are supposed to be surfaces in some like fixed manifold?
No, they're abstract surfaces. So what kind of time evolution do we have in a TFT? Well, if I just evolve on a cylinder, nothing happens because it's topological. So the only interesting time evolution is associated to topology changes. So the way to understand that is in terms of cobordisms. If M is a free manifold, it is oriented if we decompose the boundary of M, is decomposed into the incoming and the outgoing boundary. This step is actually not essential, but I find it more intuitive. So, for example, the manifold might look like this. It could be something which takes a torus on one end, and on the other side, it has a sphere. You can certainly engineer such a manifold by taking a solid torus and removing a ball in the middle. And we kind of intuitively think of one direction as time. That's only intuitive and not really part of the axis. Then the partition function of M is a linear operator from the Hilbert space on the incoming boundary and of course you want that if we compose two such manifolds, then these operators compose as well. This is the most important axiom. If I have M is with, say, M1, M2, where the outgoing boundary of M1 is equal to the incoming boundary of M2, then we can glue them together. In terms of pictures, that's just doing one thing and then doing another one. Like that.
Where do we specialize to three manifolds?
The definition makes sense in any dimensions, but because Chern-Simons theory is a dimension 3, I just wanted to focus on this example.
Sorry?
Yeah?
In your first example of torus and sphere, what's the incoming boundary? What's the outcome?
I wanted to read it from left to right, so my arrow indicates in, out, in, out.
What about the cylinder? So cylinder also has boundary.
These pictures are very sketchy because they're actually hard to draw. So the real picture Sorry about that. Sorry if the picture was causing confusion. I take like the two disk times the circle. The boundary of this is a torus, and then I remove a ball.
I see.
I think you can kind of convince yourself about, but in this picture, this direction here is going to be related to the radius in this disk, and one cycle of the torus is shrinking, and I get a singularity, and then it turns into a ball. So the most important axioms, if we have two such manifolds, then we can glue, and gluing corresponds to composition. Well, there's going to be M2. So this is an operator which goes from the Hilbert space to in, M1, and then I go to delta out, M1, which is equal to the one for the incoming boundary of M2, and then I go to delta out, M2. Okay, any other questions? Yeah.
I have two questions. So there's no, given a three-dimensional oriented manifold, will it in general have this decomposition of its boundary as distinct things?
No, so let me say, maybe I shouldn't have introduced this. This is a way I like to think about it. You can think of it as a manifold with this extra data gives you a map. But it is actually not essential. So let me say another axiom that will allow you to understand why it is not why this is not really essential. So the other axiom is that if I reverse the orientation, I change the Hilbert space of a surface to its dual. So if sigma bar is sigma with opposite orientation, then axiom 5, Hilbert space of sigma bar is equal to the Hilbert space of sigma. So that means, so if we like, we can view all boundaries as outgoing, and this reverses orientation on the incoming boundary of M, so that the partition function of M is then an element of which is the same vector space. So the reason I wanted to do it like that is I wanted to talk about composing things. I didn't really want to talk about taking partial traces, which is what you'd have to do in this picture. So I just thought it was easier to explain what composing is.
The other question is, it seems, so because we're working in 3, it really seems that the only thing you can do at the boundaries is add genus or not. So if I have two things with the same genus, will they be the same age?
Yes, because any two surfaces of the same genus are the same. This is so you can ask how much geometric structure on sigma does H depend on, and the answer is essentially none. It just depends on sigma as a topological surface. So there's a slight caveat to that, which is kind of subtle, and I don't want to get into it too much. Is that for Chern-Simons theory, strictly speaking, the projective Hilbert space depends only on sigma. The actual non-projective Hilbert space depends on some slight topological data. So maybe I've given you an overabundance of axioms. I think some of these axioms are probably redundant. But also, another important one is that the disjoint union also acts as a tensor product on three manifolds. And I should say, this fact, you can deduce it from, let me just draw, if I take my surface times the interval, where both boundaries are incoming, this implies the two outgoing boundaries if you think about the partition function for this, it's a vector. Yeah, it's a vector in the Hilbert space for the two copies of sigma with opposite orientations, and it produces through this pairing. So 5 is actually redundant if you think about it. But you know, so one could go on forever with this kind of stuff. So I hope you kind of see where we're getting to, right? We wanted to understand how do our knot invariants behave when we chop up our knot into little pieces. And this picture tells us how the partition function of a three manifold behaves when I chop up the three manifold into little pieces. So to understand the thing we really want, we need to understand the variant of these axioms for a three manifold with a knot in it. So I won't give you all the details because they're basically the same. So these axioms are what you would expect for a TFT with a defect. For a TFT, say 3D TFT with a 1D oriented defect, so very similar, except, so let's think about how, if I had some three manifold, and again, this is a heuristic picture, I had some surface in the middle, and I had, again, impossible to really draw it, I had some knots, maybe wandering around. Those knots would intersect the surface at points. Right? So, so a link intersects sigma at points which are labeled plus or minus depending on the orientation of the link. Okay, so the extra features in this setting the Hilbert space is defined for surface sigma with n plus m points. N with a plus and m with a minus. Okay, because I have some link. If the link intersects the surface n plus m times, n one way, m the other way. The 3-manifold has a link in it with boundary on the boundary of m. Okay, so the 3-manifold has a link inside it. So Z of the 3-manifold with a link is going to be a map from the Hilbert space of the incoming guy together with its the incoming boundary of the link to the outgoing guy as before. And all other axioms are the same. Except one thing is to bear in mind is that if I, so the Hilbert space of some surface with some n positive points and m negative points is the same as the Hilbert space of the orientation reverse surface, where I also switch the positive and negative points. And I dualize.
Sorry, what do you mean by the boundary of the link?
Yeah, so the picture is, we assume near the boundary of m looks like some surface times an interval, and the link looks like some points in sigma. Times an interval. So here's a little picture. If I assume, I'm going to draw a picture where I draw locally in the surface, so the surface looks like a plane. The surface look like this. I'm going to have a bunch of points, and near the boundary, these extend off in straight lines. Then as I go further away, they interact with the same direct.
So the boundary of the link is a point, right?
Is a point on the surface.
Yes.
So the boundary, yes. There's going to be some points. any other questions? So now let's get back to the relation for the Jones polynomial. And we'll see if we can, what kind of expression you'd want to have in quantum field theory for that relation to hold. So, suppose we have a link in S3, and we focus near one crossing. And then there's all kinds of other stuff happening. How do we understand the partition function of S3 with this link in terms of data, of like more local data? So the answer is, I have my two strands, which can get close to each other in 3 dimensions. What we do is we look at a little ball around them, and I remove it. My artistic skills are not really up to snuff for this class. I wanted to be imagining these guys crossing in the center of a 3-ball. So we write S3 as M1 union M2, where M1 is equal to a ball surrounding the crossing, or the two strands. M2 is the complement of M1. These are glued along S2 with 2 positive points. Okay, that makes sense, because I have this sphere, and I have 2 incoming arrows and 2 outgoing arrows in the sphere. So just by the axiomatics, the partition function can be written as a pairing between the partition function of this guy and this guy. So let Z M sorry, S3 L is equal to the inner product between and Z of M1, and I'm going to draw the crossing here. So where does this take place? Well, where the partition function for this ball with this crossing is an element of the Hilbert space attached to the 2-sphere with 2 positive and 2 negative points. And the Hilbert space for the other guy is an element of the Hilbert space where everything has been, all the orientations have been reversed, so it's in the dual vector space. So the partition function we're interested in, the not invariant for this link, is a pairing between this vector and this covector.
Did we at any point say something like that h of the empty set has to be a point? It has to be
Yes, good point.
a dimensional vector?
Yes, thank you. Yes. Sorry about that. I forgot to mention that. So now, the key point is, no matter what happens inside this region, the partition function for the link will always have an expression like this. So similarly, if we modify our link locally to this guy or this guy, then the partition function, this is L plus, M L plus, L minus, and Z M L0 has the same expression where we replace the partition function of the interior region by one of these two expressions. Any questions? Yeah.
So do we define the partition function as a map from like one boundary to another boundaries?
Yeah, sorry. This is the same point as you made a second ago. So the incoming boundary of M1 is the empty set. and the outgoing boundary of M2 is the empty set. Now, so this is I forgot in the axioms that set of the empty set is C. So if M is empty, and the partition function of M, so you probably can't see this, is a map from C to C. So it's a number. So the picture we're doing is we're doing the empty set and then turning that into a ball, and turning that into the empty set again. Sorry, turning it into a sphere, then turning it into the empty set again. So can you guys can probably see what we need to do. So the Jones polynomial says there is a linear relationship between the partition function with these three different local expressions. So we will have that for any link as long as in the Hilbert space of the two-sphere with these four punctures, there is such a relationship. Does that make sense?
We win because Z of M2, L prime doesn't depend on the crossing inside.
Yes.
So it's a linear function of Z of M1,
Yes, exactly. So it only depends on that vector in the Hilbert space of the two-sphere with 4 points. And the wonderful fact is that that Hilbert space is two-dimensional. And we have 3 vectors in it, so there's a relation between them. So what do we see? So a skein relation like in the Jones polynomial if there are functions f plus of h bar, f minus of h bar is the coupling constant, f0 of h bar, so that so that there's this linear relation. And this relation is supposed to hold in the Hilbert space for S2 with 2 positive and 2 negative points. The theorem is, it's actually not hard, we're going to see it next time. This Hilbert space is two-dimensional. Well, I have to tell you exactly what context, right? Because we have Chern-Simons theory, and we have these defects, and the defects could be associated to any representation of any group. So this is if G is SUN, and the defect is a Wilson line in the fundamental representation. So once we know this, we're going to know there are some functions such that this equation holds. It's going to be very hard to actually calculate them, but you can use symmetry properties to show that they can be related to the ones Jones uses by some change of coordinates. And we can also calculate them to leading order and H bar. It's kind of fun to, I hope to do this soon. You look at that diagram and calculate. You compare the three diagrams and the leading order gluon exchange in each of them. You'll find the leading order expression. Okay, any questions?
This part, it is not supposed to be obvious that Chern-Simons theory can be rephrased in terms of these axioms, right?
No, so it's not obvious at all, actually. So from the math point of view, that would be considered like an important theorem. So from Witten's point of view, and I suppose the point of view we're taking here to a degree is, so Witten's point of view is that he believes the field theory exists, and by definition, and a field theory for him means these axiomatics.
But we're gonna see some of these heuristics of how the Chern-Simons data and the Chern-Simons action and all of that comes into constructing this Hilbert.
Yeah, no, absolutely. So you actually kind of seen this already in your tutorial last time. So the one way to think about what the tutorial was about was I take the two-sphere and I decorate it by a bunch of points. Now these points are labeled by integers because for U1 I have a Wilson line of integral charge. And then you analyze the Hilbert space. And the answer was the Hilbert space is empty unless the sum of the charges adds up to a multiple of the level. And then it's 1.
We haven't finished.
I haven't finished. I probably got a bunch of factors of pi completely wrong.
Okay.
This one is kind of easier in some way. But yeah, and again, as we go on, I want to describe what the Hilbert space looks like for a genus G space using the Lagrangian.